Hello everybody. Right, let's keep going with earthquakes. So now let's think about measuring earthquakes. So how do we measure the size of an earthquake? Well, we can look at a couple of different factors. We can look at the intensity, and that's going to be a measure of the degree of shaking at a given location based on the amount of damage. And now this isn't a particularly reliable measure, and we'll discuss why in just a second. The other option we can use is the magnitude, and magnitude estimates the amount of energy released at the source of an earthquake, and this is far more reliable. So let's look at the intensity scale. So one of the primary techniques for measuring intensity is the modified Mercalli intensity scale, and you can see it here. It goes from 1 to 12, and if we just pick any of them, so let's go with number 5. So felt by nearly everyone, many awakened, disturbances of trees, poles and other tall objects sometimes noticed. Okay, so question then becomes how do you know whether many people are awakened? What would you describe as a disturbance? Okay, what would you even define as tall? So as you can see, this particular scale is very, very open to interpretation. And of course, the other problem is that the level of damage will vary depending typically on things like building regulations. So somewhere like San Francisco or Los Angeles, for instance, that have pretty robust building regulations for modern buildings, well, those modern buildings are going to be able to stand up to an earthquake far, far, far better than countries that have lower building standards. So once again, that would mean, in a country that has relatively low building standards, damage would typically be quite heavy. And so obviously that would imply that you would be at you'd be towards the higher end of the scale. In contrast, an equal-sized earthquake in Los Angeles would probably cause far less damage, and therefore, based on the damage you would see in Los Angeles, you would assume you'd be somewhere towards maybe the middle of the intensity scale. So the intensity scale is an extremely subjective thing, and it's affected by variables like building codes. So is the intensity scale any good? The answer is no. It's pretty useless. Alright, so let's think instead about the magnitude. So the magnitude, if you remember, estimates the amount of energy released at the source of the earthquake. Now the first method of essentially measuring magnitude is the Richter magnitude, and of course this is the one we're all familiar with. So so when there's been an earthquake, also they'll typically say on the news it was let's say 7 on the Richter scale. Okay, now the Richter magnitude uses the amplitude of the largest seismic wave recorded during the event, and it's a 1 to 10 scale. Although typically above 7, it does become a little bit unreliable. The other method we can use is called the seismic moment, and the seismic moment is based on the amount of displacement along a fault. Now we can measure that using a satellite. So once again, it's a scale of from 1 to 10, and essentially for each increase in the scale there's a 10-fold increase in amplitude, which essentially equates to a 30-fold or 30 times more energy. So so going from step 1 to step 2 is a pretty significant jump in the amount of energy being released by the earthquake, and so on from step 2 to step 3. Once again, the amount of energy increases substantially. Okay, so here's the Richter scale. So the Richter scale, essentially, as we've discussed, focuses on the amplitude of the largest wave. Okay, so what can we see? Well, if we look at this pretty simplistic diagram here, what do we have? Well, over here we have the energy released. Okay, this is equivalent kilograms of explosives, so not really a classic scale for measuring the amount of energy released, but hey ho, it's what we got. And over here we actually have the earthquakes themselves and the magnitude from 1 to 10. So we can see that the scale itself gets broader as we come down. So that this essentially, because the amount of earthquakes is increasing, so you can see magnitude 2 earthquakes, okay, we can expect, somewhere in the region of 1 million of them per year. So they're super common. In contrast, something with a magnitude of around 9, we could expect essentially 0.1 or less than 0.1 of them every year. So those earthquakes will be, on the whole, pretty rare. Okay, so number one, as the magnitude increases, the number of those earthquakes you'll experience each year gets lower. Okay, and obviously as the magnitude increases, the amount of energy released increases. So the Richter scale, it focuses on the largest amplitudes, and essentially they equate the amplitude to the amount of energy released. Now, it's a logarithmic scale, and one of the problems with the Richter scale is that you need to make adjustments to compensate for essentially the distance between the seismographs and the epicenter of the earthquake, but also the types of rock that the seismic waves are moving through. So the Richter scale was designed for the San Andreas Fault in California, and it was designed for seismographs at a set distance from the San Andreas Fault. So when an earthquake occurs on the San Andreas Fault, it was supposed to be measured by seismographs which were at a set distance from that fault, and obviously they knew the types of rock that the seismic waves were passing through. Now, in other parts of the world, when an earthquake occurs, well, number one, the seismograph, so the seismic monitoring station, may not be at that set distance from the hypercenter. That's the first problem, so the distance might be different, but also the types of rock that the seismic waves have moved through will also very likely be different. And so this means you have to start adding corrections to try and work out what your Richter scale is. And of course, some of you might know, when you start adding corrections to try and make things work, well, that means your data can get a little bit dodgy, shall we say. So the Richter scale is a great idea, but it's only really designed to work in California. As soon as you take it outside of California, you have to start essentially adding fixes to the data to make it work. So what about the seismic moment? Well, the seismic moment is based on the fault rupture and the average amount of slip and the force that was required to overcome the friction sticking the rocks together, essentially, that were offset by the fault. So the seismic moment, essentially, the formula is MO, that's the seismic moment, is, and now I can't remember at all what letter this is in Greek, multiplied by A, multiplied by D. Now the shear modulus, which is this Greek letter which I can't remember, slightly embarrassing. Now that one's quite easy, because depending on what type of material you're dealing with, it can be one of two numbers. In the crust, it's going to be 32 gigapascals. In the mantle, it's going to be 75 gigapascals. So that one is quite easy. So just insert to the correct number depending on where you are. So A is going to be the area, and that's simply going to be the length multiplied by the width. Okay, so if we look here, here's our rupture of our fault. So obviously we have the length of our rupture and the width of our rupture. And then we have D is going to be the average displacement during rupture. Okay, so these two are relatively easy. The displacement is relatively easy because we can measure that from satellites. And the area can also be calculated relatively easily because we can work out, once again, the length of the rupture, also from satellites, The width is a little bit more difficult, but that can also be found out relatively easily. And so the seismic moment is a far more realistic measure, because it doesn't matter what rocks you're dealing with or how far your seismograph was from where the earthquake occurred. You're focusing on the fault itself, not the seismograms. Okay, so let's compare the Alaskan and Chilean earthquakes. So here we have the Richter scale, and here we have the seismic moment. So we're going to compare them using the different techniques. So in terms of the Richter scale, the Chilean earthquake of 1960 gave a value on the Richter scale of 8.5. The Alaskan earthquake of 1964 gave a Richter scale value of 8.6. So it was bigger. So, okay, based on the Richter scale, the Alaskan earthquake was larger. What about the seismic moment, though? Well, based on this, the Chilean earthquake was actually larger, because the seismic moment is 9.5. In contrast, the Alaskan earthquake, 1964, produced a seismic moment of 9.2. So the question is, why does the Richter scale say the Chilean earthquake is smaller, but the seismic moment says the Chilean earthquake is larger? So the reason is, once again, it's all down to the types of rocks and the distance of the monitoring stations from the earthquake itself. So the reason is the Chilean earthquake released more energy, but in the Alaskan earthquake, the energy was transmitted more effectively through the earth. So this means that essentially 100 kilometers from the earthquake itself, this is typically where the monitoring station should be located for the Richter scale method. Okay, so you want your monitoring stations to be 100 kilometers from your earthquake. Well, because the seismic waves are being transmitted through the earth very efficiently in the Alaskan earthquake, it meant they moved through the earth and they didn't lose much energy. So when those seismic waves hit the monitoring stations 100 kilometers from the epicenter of the earthquake, well, in that case, in the Alaskan situation, it meant those waves were quite powerful. In contrast, the Chilean earthquake, well, as those seismic waves moved through the crust, they didn't have such an easy time. So that meant they were losing energy because they were having a more difficult time. And that meant by the time the waves arrived 100 kilometers from the epicenter, well, it meant they had lost more energy. So they weren't quite as big as the Alaskan earthquakes. Now this means the amplitude is going to be smaller. So the Chilean earthquake will have produced lower amplitudes than the Alaskan earthquake. Hence the fact that the Richter scale says the Alaskan earthquake was the larger one. Now when we use the seismic moment, obviously that gives us a completely different reading, because we are then looking at the fault itself and the amount of energy released by that fault movement. And so based on those measurements, the Chilean earthquake was actually noticeably larger. So, depending on what technique you use, you can get different answers depending on the exact situation. So the Richter scale, as mentioned, it's dependent on the types of rocks that your seismic waves are moving through and the distance of your monitoring station from the earthquake itself. You would typically want your monitoring station to be about 100 kilometers from the focus. However, if that's not the case, obviously you need to apply essentially fixes to the data to make it work. So in terms of earthquake events themselves, what do we see? Well, we tend to see graphs that look something like this. On the graphs you will see the main shock. Well, that's actually the earthquake itself, and that will typically be when the greatest magnitude of energy is released. So you can see on this graph here, here's this point up here, this is going to be the main shock right there. Now, before the main shock, you have what to refer to as foreshocks. So these are small earthquakes that precede the main shock, and these small earthquakes, they can range from a few days before the main earthquake to years before the main earthquake. So, foreshocks aren't particularly helpful when trying to predict if a major earthquake is about to occur. So, then we have aftershocks. And aftershocks are the result of, once again, smaller earthquakes generated after the main event. Now, aftershocks, as you can see, are more common and typically a little bit larger. And that's because the fault movement that's being produced by the main shock essentially allows other parts of the fault to then move. And obviously when those other parts of the fault move, well, they produce little earthquakes of their own. So this added fault movement, as we can see here, is reflected in the higher number of earthquakes and the increased intensity versus the foreshocks. You can also see it here on this diagram. Obviously the main shock is going to be the largest magnitude. Aftershocks will occur after the main shock, and foreshocks will occur before the foreshock. But you can see the difference one more time. Foreshocks tend to be lower magnitude and relatively, sparse in number. Then we have the main shock, which has the largest magnitude. And then we have the aftershocks, which tend to be more numerous in number, and they'll typically have a higher intensity when you compare the aftershocks to the foreshocks. So, what kind of destruction can happen after an earthquake? Well, obviously in terms of the earthquake itself, it's going to cause significant damage to buildings and infrastructure in general. So one of the major risks of an earthquake is actually fire. It's not one of the ones you would think of, for an obvious point of view. Now, it's very, very common because what tends to happen is gas mains get broken. So, imagine the situation, you've just survived an earthquake, you've stumbled out of your house to see the destruction all around you. What do? Well, if it's, your particular, fancy, you light a cigarette to calm your nerves. You light that cigarette and, of course, there's a broken gas line near you. You can guess what happens. So, it's not uncommon for fires to start after earthquakes. There are also other risks associated with earthquakes, such as tsunamis and other forms of flooding. So earthquakes, obviously you've got the building damage, fire risk, tsunamis, other forms of flooding. Obviously water pipes can get broken. This can mean contaminants can get into the water supply. That can be anything from chemicals to things like raw sewage can get into the water pipes. And then of course you have the problem then of your municipal water being contaminated, and obviously then you'd have to switch to hopefully another cleaner source of water. So how do we try and limit the risk from earthquakes? Well, the first thing is we produce these things, and they're called hazard maps. And so as we can see, we can look at this map and we can see the different ranges of hazard essentially. So we can see we have greatest risk marked out here in red and lowest risk marked out here in kind of beige. Okay, so we can see relatively low risk over here and relatively high risk right here. Now this is helpful because it allows the authorities to plan. So the authorities know that in all likelihood the highest chance of an earthquake is going to be in this area right here. Now this means they know essentially where they would be focusing their efforts in terms of rescues, and it also allows them to plan in advance. It allows them to make sure that things like the gas mains, the piping, maybe are a little bit more resistant to movement. Out here, on the other hand, when you're laying water pipe or gas pipe, you don't have to worry about that anywhere near as much. So you can take that in, you can take construction code into account in this region as well, and try and help to protect buildings in that way as well. So when it does come to buildings, obviously you can improve your building design. Okay, so there are literally some buildings in San Francisco and Los Angeles where the building isn't actually on a foundation. It's literally on springs. And so when the earthquake occurs, the building will wobble on those springs, but essentially the movement caused by the earthquake will be accommodated by the springs and the movement of the building. So the building will actually move with the earthquake, so it won't break. You can also do other things, like you can, increase the amount of structural support inside your buildings, making them essentially more robust. And there's a whole range of other things that you can do to make your buildings stronger to earthquakes. So one of the things you can worry about is just make your buildings better. Now, obviously, that doesn't do any good against things like tsunamis and flooding, but it does get around one of the main problems, which is things like building collapse. You can also make sure you reinforce your gas supply lines and your water piping to, once again, try and limit any damage to those caused by an earthquake. So, tsunamis. So why do tsunamis occur when it comes to earthquakes? Now, there are a couple of videos here, okay? And this video is actually quite a good one when it comes to explaining what happens with regard to tsunamis. Now, we're going to use these diagrams here. So what we have is we have ourselves a convergent plate boundary. So this is our subducting piece of oceanic crust, and this is our overriding piece of continental crust. Now what happens is, as the oceanic crust subducts down, we have friction here. And so what ends up happening is the front portion of the continental crust here starts getting pulled down with the oceanic crust. So as the oceanic crust subducts, it literally starts causing the front of the continental crust to warp downwards. And well, then you can guess what's going to happen. Eventually, friction is going to be overcome, and the continental crust is going to snap upwards like that. It's going to snap back to its original position. Now, what's that going to do? So, as this piece of continental crust bounces back and snaps back to its original shape, it's going to push the water above it upwards. And it's going to create, essentially, a feature like this. And then what's going to happen is this feature is going to split into two directions. Half of the feature is going to go this way into the open ocean, and the other half is going to go this way towards land. Okay? And so this is the risk that island chains associated with convergent plate boundaries have when it comes to things like tsunamis. So countries like Japan, for instance, are very prone to these kind of features, these kinds of risks. And so once again, it's just caused by the front of the continental crust being pulled downwards due to friction, and then that eventually, when friction is overcome, the elastic strain is released, and the front of the continental crust will just snap back, and it essentially pushes up the ocean. And then essentially this pushed up pushed up area of ocean essentially splits in two directions. Half of it goes into the larger ocean itself, and the other half goes back towards land. And it's the other half that's going back towards land which is more dangerous, obviously, because it is going to cause a tsunami which is heading straight towards land. Now, this part of the tsunami is going to go out into the ocean, but eventually, if it keeps going, it is going to find land. And when it finds land, it can also cause a tsunami there. Okay? So you can have a situation where earthquakes on one side of the Pacific can cause a tsunami on the other side of the Pacific. That's how far these tsunamis can travel. Now, the tsunami itself, actually, when it moves through open water, it's actually not that high. It'll cause the water level to maybe rise up by a few feet as the wave passes through. It's only when the wave starts to hit, or essentially starts to get into shallower water, because as the wave starts to get into shallower water, it starts to build up in height. So that means as the wave starts to get near the coast, the height of the wave starts to get bigger and bigger and bigger. And so eventually, when your wave is in very shallow water, it's very, very high. And that's our tsunami. So let's look at a few examples. Okay. Now, I'm not going to try and pronounce that because I will get it wrong. So this is a Japanese earthquake from 2011. Now this one is very, very large. It's 9 on the Richter scale. And it was essentially, we have an earthquake associated with a subduction zone beneath Japan. So here is though in this case it's going to be the epicenter. And this, you can see here, is the trench right there. So we have the Pacific plate is subducting westwards underneath this bit of crust here. And friction is pulling down the front of this piece of crust once again as the Pacific plate subducts westwards, and this is the piece of overriding crust. It's warping it down. It's making the piece of continental crust bend down at the front, and as discussed, eventually friction will be overcome and the continental crust will snap back. And as we said, that will push up the ocean, and that will then split in 2 directions. One half goes into the open ocean, the other half goes back towards land. Obviously, as it goes back towards land, eventually that will lead to a tsunami. So this caused just under 16,000 deaths, so it's a very, very big event. And essentially there's the displaced seafloor essentially popped upwards, and it formed a destructive tsunami that damaged the Fukushima nuclear power plant. Essentially, I believe it's the second worst nuclear disaster after, of course, Chernobyl. And you can see the destruction caused by the tsunami. So not only did the tsunami itself, essentially damage buildings and farmland and, infrastructure close to the coast, but it also caused essentially a large release of nuclear material from the Fukushima power plant, which essentially has contaminated the surrounding area. So it was a extremely, extremely damaging earthquake with a very, very high loss of life, unfortunately. In terms of the part of the tsunami that actually went out into the open ocean, you can see this is it spreading out over the Pacific. And so you can see essentially over time it's moving further and further away, and it will actually lead to the formation of tsunamis, sometimes at great distances from the earthquake itself. Now these tsunamis will be a lot weaker, okay, and a lot smaller, but nevertheless they will occur. Okay, so do you know what? This is a great place to stop this video. So once again, stop the video, get up, have a walk around, have something to eat maybe, have a glass of water, some coffee, some tea, and then when you feel ready, come back for the next part.